The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to this CPD. My name is Andrew Ogden and I'm a Senior Engineer at Kingspan Environmental. I have 16 years experience of building services as well as being a Chartered Engineer covering domestic and commercial design. I would like to talk to you today about solar thermal technology and its application. The seminar is approximately 45 minutes long with a chance for questions at the end, so I hope you enjoy the presentation and also give you a better knowledge of solar thermal. The agenda of this presentation is to cover a bit on the Kingspan Group, what is solar thermal energy, when and when not to use it, terminology and application, what factors affect a solar thermal system, how to design and size an effective solar thermal system, solar collector types, collector mounting options, legislation and regulation, and government funding. The aims of the presentation: is solar thermal effective, types of collectors, application, legislation. Let's start with a bit about Kingspan Group. Kingspan Environmental is a division of Kingspan Group plc, one of the world's leading providers of sustainable products and services. Part of the plc is Kingspan Panels, Kingspan Insulation, Kingspan Environmental, and Kingspan Access Flooring. The revenue of the plc is 1.6 billion euros and the trading profit is 107 million euros. What is solar energy? Solar energy is a renewable, an energy source that does not deplete the Earth's natural resources and does not create waste products. It's sustainable. The provision of energy such is that it meets the needs of the present without compromising the ability of future generations to meet their needs. Why to use solar energy? The environment solar energy enjoys many environmental and economic advantages over other forms of energy currently used. The benefits are: it's non-polluting, therefore it produces no emissions; non-consumptive, so limitless resources; going green, which is a PR advantage; free heat production and generation. The amount of CO2 produced to generate the equivalent of 1,836 kilowatt hours of natural gas is 180 grams per kilowatt. CO2 emission from oil is 238 grams of kilowatt hours. CO2 emissions from electricity is 459 grams, and solar is 0. Why use solar energy? It's economical, therefore it's cost effective, immediate savings, easy accessible, price of solar doesn't fluctuate like gas, electric and oil, and legislation. The EU and GB Irish legislation which needs to be met. Is solar thermal a viable energy source in the UK and Ireland? Well, the answer to that is yes. The UK's daily solar irradiation is 3 kilowatt hours per metre squared, equivalent to approximately 130 litres of oil per metre squared per year. So therefore, yes, it is a viable source. Why use solar energy? Fossil fuels are a limited resource, however solar energy is replenished every single day. As you can see from the diagram, there is only so long we can rely on natural fuel resources. Simple ergonomics, supply and demand, dictate that resources deplete and become more valuable. Cost of energy from fossil fuels can only increase in the future. Traditional fuel resources such as coal, petroleum, nuclear and gas, as you can expect, will eventually deplete. We'll have no increased use of renewable energy, as well as more importantly reduce our energy requirements. And one of the key ways we can do this is by increasing the quality in the way we design and construct our buildings. Solar thermal energy. Solar thermal technology uses a solar hot water system to collect energy from sunlight and use it to heat the water. Here's an example of a solar system in operation. A is a solar collector. B is the pump set. C is a hot water storage cylinder. D is the boiler. E is a hot water draw-off to your taps and baths and showers. F is a solar controller. And G is the expansion vessel on the system. As you can see, the panels heat the water through the coil, heat transfer, and distribute off into your outlets. All the components work together to heat the water from the sunlight. The expansion takes relief from the system. The pump pumps the water glycol round the actual system through the coil, heat transfer. You can also have a boiler which supplements the actual source as well. When is solar energy not recommended or appropriate? Well, solar energy is not recommended if you've got extreme high altitudes on your system. Physical location, therefore if your building is north facing or it has significant overshadowing from trees or other buildings. If there's non-consumption during peak periods, therefore if you are retaining most of the energy during days when you're not going to be using a hot water outlet, and insufficient room for the water storage, you require water storage to actually transfer the heat across. Terminology. Here's some terminologies which are used when discussing or designing or talking about solar thermal systems. The absorber plate. This is the black surface in the collector that absorbs the solar radiation and converts it to heat energy. Absorbance. This is the ratio between the radiation absorbed by the surface, the absorber, and the total amount of solar radiation striking the surface, solar yield. Array. An assembly of solar panels assembled for specific application. Azimuth. The angle distance between the south and the point of the horizon directly below the sun. Orientation. TESOL. A computer program for simulation and design of solar thermal systems. Diffuse radiation. Indirect sunlight that's scattered from air molecules, dust and water vapor. Direct radiation. Solar radiation that comes straight from the sun, casting shadows on a clear day. Solar constant. The average intensity of the solar radiation reaching the Earth outside the atmosphere equal to 442.4 BTUs per hour per square foot, or 1,395 watts per meter squared. Solar fraction. Percentage of demand supplied by solar thermal system. Barham getter. A getter maintains a vacuum by absorbing any remaining gas molecules present in the collector tube after we have pulled the vacuum. We use a barium sulfate coating that is vapor deposited on the glass. What factors affect solar thermal systems? The diagram shows the influence the orientation of the solar panel has on the annual gain. It can be seen between the best and worst orientations. The annual energy consumption can be nearly halved. The energy contribution will decrease towards a steep incline and large deviations from the south orientation. The optimum position for solar thermal panel would be due south on a slope between 30 and 40 degrees, as you can see here. Collector area, storage volume and domestic hot water demand all affect the performance of a solar system. The collector area, the larger the area, the more solar energy can be collected. Care should be taken to not oversize the system. Storage volume, the larger the cylinder, the volume, the larger the thermal store. Direct hot water demand, the larger demand, the higher the solar energy consumption. What factors affect a solar thermal system? Well, weather also and location makes a big factor on the solar system. As you can see from the diagram, the closer you are to the equator, the more efficient the system becomes. Average solar radiation on a collector surface is measured in kilowatt hours per meter squared per day. In Northern Europe, Zone 1, it's between 2.4 and 3.4 kilowatt hours per metre squared per day. Zone 2, Central Europe, 3.4 to 4.4. And 3, Southern Europe, 4.4 to 5.4. How to size a solar thermal system. You need to determine the hot water requirement, calculate how much volume you need to store, calculate solar collector area, determine roof area and collector layout, select size and components. All these systematic steps are used to size a typical solar thermal system to generate hot water. These calculations are all done by a competent engineer or solar provider, so you don't need to worry about the technicalities, but just take you through the theory. First, we need to determine how much hot water the building requires. This is given us by our base load. A typical domestic 4-person house will have a daily hot water demand of 4 times 50 litres per person per day. That's 200 litres per day. We then calculate how much volume needs to be stored. This is worked out by 2 times the direct hot water demand for a more exact figure by formula seen here. The collector area is then calculated by the formula or by a T-SOL calculation which we provide through our consultants. So therefore, we now know our volume storage and require optimum solar area. We're now need to check that we have space on the roof to mount the collectors. We then size and select the other components. The sizing of these components is undertaken also by our ME consultants. These are what some of the components that make up the system look like. On the left hand side, you've got the solar pump station, which has got a pump inside which pumps the glycol solution from the cylinder through the panels and back through the system. This is an expansion vessel. This expansion is added to the system. This allows for heat expansion on the system. This is a hot water storage cylinder, a twin coiled solar version. The bottom coil is for solar input and the top one is for our boiler input. This is a controller that is located within the property which monitors the usage of the solar. Right, there are 2 main types of solar collectors. We have a flat plate system, as you can see here, and we have a vacuum tube, also known as evacuator tube. The models for these are, this is the FPW flat plate, and you also get the Varisol or Thermax option in the evacuator tubes. We will cover both types of collectors and briefly explain how they work. The difference between them are the respective advantages and disadvantages. I can also email you information on the products after this presentation. Flat plate collectors. So first we will discuss these. There are 2 fundamental types of systems. You have a riser system, shown here, or a serpentine system, which is shown here. There is not a huge amount of difference in the effectiveness between the 2 systems. A flat plate collector is typically constructed of an aluminium frame. Within the frame they have layered constructions, as you can see here. This construction is made up of glass plate at the top, a selective coating to absorb the solar energy, an absorbent plate transfer the energy to medium, a fibrous insulation, a hardboard insulation, and a metal sheet which is located at the back to hold all the bits in place. This is the FPW panel. Here are 2 examples of domestic flat plate installations, so you can see them in situ. You've got an in-roof installation here. This shows the panels in a cassette located under the tiles for a flatter finish. This is the on-roof installation, which is put on a frame, which sits on top of the tiles, as you can see. This is another installation. These are on an A-frame scenario. This A-frame can be angled to whatever angle you require for the optimum solar energy. Obviously, it needs to be used when installed on a flat roof. What is the effects of cold weather, wind, rain on a flat plate collector? We will list the main advantages and disadvantages of each type of collector later. However, we need to look at the construction of the two types of collectors and whether outside factors such as cold weather, wind, rain can affect their performance. We are obviously more susceptible in the UK and Ireland to such weather conditions than the southern European countries. The diagram shows what happens when the energy from the sun hits a solar collector. Energy can be displaced by reflection of the glass, here, by convection off the surface of the collector, here, and by conduction through the structure of the collector, here. The flat plate collector in particular, due to its construction, is affected by low outside air temperatures. The lower the air temperature, the higher the heat loss from the collector. Its performance and efficiency is greatly affected by cold weather, wind and rain. Now we can move on to evacuated tubes. There are two types of solar vacuum tubes, heat pipe and direct flow. These are evacuated tubes built into a header. These are mounted on a frame and they're connected in through the header. The header is then connected onto your system, through your pump set, to your store or to your cylinder. This is the cover of the header, a foam installation, condenser manifold, condenser socket, end connection, retaining strap. I'll show you some more details on the next slide. The Thermax vacuum tube collector is made up of a glass tube. It's got a rubber end bumper on it. It's got a vacuum area in it. That's why it's called a evacuated tube. It gets more efficiency out of it. It's got a selective coating, which obviously improves the performance. It's got a soda lined glass, a flexible net for installation, the condenser head, which fits into the condenser header, which I showed you on the previous slide, the heat pipe which runs through the evacuated tube, the getter, which I mentioned earlier, the copper absorbent plate, which is what transfers the heat. Our heat pipe has a feature that makes it unique when compared to any other evacuated tube on the market. It has a normal operation and a limiting temperature. This moves through condensing. Here are two examples of vacuum tube installation, so you can see what they also look like in situ. This is on a frame, obviously on a flat roof installation again, built into a larger header, distribution pipe work through to the system, and this is installed on the roof as a collector. As shown previously, the Thermos is a unique built-in thermal limiting device. The device is open and heat transfer occurs until the condensator reaches its set point, moving up. The snap dip operation and close the device, stopping heat transfer into the condenser. The device reopens as temperature falls below the set point, reactivating heat transfer. The heat pipe collector, unlike the direct flow collector, is decoupling from the internal solar system. Therefore, you can remove them from the header if there's any damage or one's not working or anything like that, so you can actually click them back into the header. The solar energy is transferred by the means of evaporation and condensing. Within the tube there is a small amount of heat transfer medium. Upon heating, this medium evaporates, travels up the tube to the condenser. The internal solar system, water travels across the condenser in a manifold. It absorbs the heat from the bulb and transfers the energy into the coil of your cylinder. The heat transfer medium condenses and runs back down the tube. This cycle repeats itself continuously throughout the day to generate heat from your solar system. Here are two examples of the concentric tube in situ. A concentric tube is used with a direct flow collector. This is a tube within a tube. These can be situed horizontally, flatly, because it's a different sort of scenario. The cooler heat transfer medium travels down the outer pipe in the tube and is heated by the sun through the absorbent plate. The warmed medium then flows back through the central tube, back to the manifold, and then in turn back to your cylinder. This is a slightly different installation. So what is the effect of cold weather, wind, rain on evacuated tube collectors? Due to their insulation properties, evacuated tubes work very well in climates with diffuse sunlight and/or air temperatures such as the UK and Ireland. Each solar collector consists of highly insulated manifold and a row of solar tubes. The vacuum inside the tube provides perfect insulation and therefore protects the system from outside influence such as cold, rain and windy weather, or even high humidity, giving it an extra performance in these conditions. Advantages and disadvantages of flat plates. Advantages of the flat plate system. It's a lower cost, can be more easily integrated in the fabric as shown with the in-roof and on-roof installation. Disadvantages. Low performance through conduction, convection and radiation, therefore you may need more surface area of collectors. Higher wind load requirements. Basically the wind can get underneath the panel and create it like a sail. Glass and absorption can get dirty and affect performance. Higher volume content equates to larger component sizes, i.e. expansion vessels, quantity of glycol, and it isn't efficient in low light. Vacuum evacuated tubes, advantages and disadvantages. The advantages are it's higher solar yield than flat plate collectors with the same absorb area, 30% more efficient, they are better in SAP, and they create better SPEM results. There is little thermal loss, only through small amounts of radiation. As the tube is sealed, dirt or moisture cannot get into the collector. They work in cold, windy and humid conditions. Individual tubes can be rotated to optimize the ideal orientation through 20 degrees. High temperatures can be achieved. The disadvantage of the evacuated tubes is they are more costly. They are also not easily integrated into the fabric of the building, i.e. they cannot be put on in-roof installation kits. They are only available on roof only. Here's some examples of mounting options. The flat plate and heat pipe type evacuated tubes require minimum pitch of an angle of inclination of 25% to work correctly. Direct flow evacuated tubes can be installed almost in any orientation. Flat plate and heat pipe collectors, positions 1, 2, 3. So flat plate can be put on the roof. Example here as well. As shown here. The direct flow collectors can be put in any orientation. They're the evacuated tube direct flow collectors. They can be put on the side of walls, on roofs, pitch roofs, and then put on an A-frame on a flat roof. Therefore giving you a bit more flexibility when installing into a system. talk a bit about legislation and solar thermal. We'll just cover the main points of each of these pieces of legislation, and if you require more information, I am happy to send that across after the seminar, along with any other information required from this seminar. The 2007 Energy White Paper sets out the government's domestic and international energy strategy. It aims to tackle both the challenge of reducing carbon dioxide emissions to combat climate change, and also the issue of reducing our dependency on imported fuel. The European Energy Performance of Building Directive. This legislation came into place in 2006. The aim for both individuals and businesses is to greatly affect awareness of energy use in building, and is intended to lead substantial increase in investment in energy efficiency measures within these buildings. Code for Sustainable Homes. The Code for Sustainable Homes is a national standard for the sustainable design and construction of new homes. It is aimed to reduce carbon emissions, promote higher standards of sustainable design above the current minimum standards set out by building regulations. The code also gives a new home buyer better information about the environmental impact of their new home and its potential running costs, and other builders and tools which indifference themselves is a sustainable term. EPCs, Energy Performance Certificates. An energy performance certificate contains information about how energy is used at home or in business, along with details of how much energy used actually costs. An EPC is a legal requirement in certain situations and is a good idea for pretty much everyone, as it contains recommendation reports which suggest on how you can reduce the amount to spend on energy. Legislation will encourage householders to install renewable technologies to add value to their properties when they are moving and save them money on their energy bills, as well as reducing carbon emissions. Part L building regulations. In order to reduce CO2 emissions, the government has introduced legislation which states that all bodies installed in UK and Wales should be SEDBUG rated band A or B categories. This legislation has been a key driver, resulting in the UK becoming the largest market for condensing boilers. Here's some solar thermal applications other than what we've discussed already. Solar thermal can be used for domestic hot water, heating support for pools as well. The collectors here will generate heat, put into a plant which then distributes the heat into a swimming pool. This is a large-scale heating district hot water. This will create district heating to a large area for hot water generation. And it can also be used for industrial heating, cooling and process heating. Alternative applications. As discussed, we can use this for district heating. This is an example of a installation in Denmark. This is the largest solar thermal installation in the world. Thermax collectors are on one of 5 different collectors. After completion in 1996, the size was 8,000 meters squared. It is now expanded to 18,000 meters squared. This is a large collector area which is used again to supply district heating to an area. This is an example of an installation in Bradford for Bradford City Council. There is 12 metres of Thermax HP 400 evacuated tubes. That's 120 tubes in total. The annual gas saving of this is 780 metres squared cubed. Annual CO2 emission avoided is 1,650 kilograms of CO2. And the annual solar contribution is approximately 7,000 kilowatt hours to direct hot water heating. We did an installation at Centre Parks. That's 114 square metres of Thermax tubes again. This gives an annual gas saving of just under 10,000 metres cubed. An annual CO2 emission avoidance of just over 20,500 kilograms. That's an annual solar contribution of approximately 56,000 kilowatt hours to the direct hot water heating. As you can see, the effects on this is significant. This shows how in the schematic version, how the system is working. You've got the panels into a heat exchanger, through to a buffer vessel, through a heat exchanger again, then distribute off to the system. This is another installation that we've done. It's for NHS in Blackburn. It's got 6 square meters of evacuated tubes, a 500 litre twin core cylinder. This is a 30% annual solar fraction. The CO2 emission saving is just under 1,000 kilograms per annum. This gives you a 460 meter cube annual gas saving. That's 3,850 kilowatt hours annual solar contribution to the direct hot water system. As you can see, the panels here into a twin core cylinder. Gas boiler is firing into the top of the cylinder and distributes off through to your hot water usage systems. How the system works is the renewable goes into the bottom of the cylinder, using as much of the solar energy before any form of gas or fossil fuel is used to top up the water. On most, on quite a few days, there'll be no need for the gas installation. Most of the water will be generated from solar, but to reach 60 degrees, or if you want higher temperature water, then there will be potentially a gas input into it. But this only activates when this temperature here is below the required set point. It's an ideal care home. This shows you a bit of information regarding cost saving in monetary value, installation costs on the RHI, the money you get back from the RHI tariff. It's the outputs from the RHI savings. This calculation will be carried out. It shows obviously your net cash contribution back over the 20-year period. How the initial installation cost is down here, breaks even towards a 9-year period, and then from then it's a profitable installation. Similar sort of situation. This is a swimming pool. It also shows you what we can create as a calculation which shows you your saving financially and also your energy saving. It's the capital cost of the installation. It shows you your solar yield, your energy saving per kilowatt hour per annum, maintenance cost, tells you offset for your CO2, size of your installation, and then your payback for your RHI. Solar system design. This is an example of a solar system design. We carry out the designs for you. It gives you your RH information, your panels. Obviously, this is a different sort of scenario. It's got a loading station in it, then pumps through to your solar buffer. This can distribute off to heating, hot water. There's different variations of these thermal stores. This also allows it to be installed on commercial use, not just on domestic use. With the larger pump stations, heat exchangers in it. It's a very flexible system, but the key to it obviously is you're generating your free solar energy, which saves obviously your fossil fuel costs. Here's some of the solar system designs we can create for you, different variations, commercial use, dual buffers, cylinders, domestic, all different variations. You can use solar thermal to benefit your system and make savings. Kingspan Environment Design and Support Services. We would support sizing and product selection. We would produce a full system design and a product integration. Proposal to review and also for approval for local authorities and planning applications. We manufacture and deliver the products. We offer installation support from a few approved installers contractor list. And we also service and maintain the system. All of this is like the package that we offer as a manufacturer. We also have a consultancy that we use. All our designs, support and services will be offered by dedicated consultants. They are part of the Kingspan Group and they are experienced in M&E design consultancy. At the end of it, I'll also give their details out so we can offer you the services moving forward. Well, thank you very much for your choosing our seminar. I hope the seminar has given you a good understanding of solar thermal technology and its application. I'd just like to recap on what we have learned today. We have looked at solar thermal energy, why and when it's used, and it is also looking at when it's not suitable. The factors, efficiency and efficiency of the solar thermal system, such as orientation, inclination and geography. The process of design and sizing the solar thermal system. We've covered the two main collector types, flat plate and evacuate tubes, what they look like, their differences, their advantages and disadvantages of type of collectors. We have been through some examples of alternative applications of solar energy, such as solar cooling, district heating. We have covered legislation, regulation and government funding. From this seminar, we hope you are able to feel comfortable in specifying solar energy in a product and the advantages and disadvantages between the two types of collectors. Apply knowledge of what factors affect the efficiency of a system to be able to specify the effects of it in a project. Gain new perspective into alternative applications of solar energy. Demonstrate a knowledge of different government legislation and the grants that are available to you. Thank you very much for your time. And as mentioned before, if you would like any information or literature, please let me know and we'll arrange for this to be issued once obviously we've got your details. Thank you very much.